Okay, so we have learned some of the tech. We are now learning some of the techniques that can efficiently use the data in deep learning. Okay, so and in previous lecture, we learned about the knowledge distillation. So I mean, there are two networks, which is the teacher and the student network in this knowledge distillation. And the teacher network is already pre-trained using rich information. And we want to guide the student network. This is the network we want to train, newly train. So now the objective of knowledge distillation is to guide the training of the student network using the teacher network. So we somehow encourage student network to mimic some aspect of the teacher network. So this is the pipeline. Okay, so this is the student and this is the teacher already pre-trained. And here student network gets the hard prediction rules from the ground truth. So this is the same as the standard cross-entropy rules for the image classification. But from here, it gets some soft prediction rules from the response of the teacher network. So somehow we are making the student network, their output, close to the outputs of the teacher model. Okay, are you guys following this? Okay, and I said that by doing this, there's some the student network can learn some of the dark knowledges in the teacher network. Okay, so if we use only the ground truth, it has only the binary values, right? So only correct labels are having the 1 and all others are having 0 for the classification task. But the teacher model's output, there it has some continuous value across all the class, okay? And we can somehow encode some similarity between the classes. So we can capture some confusing classes by using this teacher model's output. So that kind of information is called as the dark knowledge, and the student network can learn about that. And next thing we learned is the hint. So especially when the student network, it has the deep architecture. If the student network getting deeper, the original knowledge distillation that applies this L2 laws in the last layer only sometimes fails. Okay, so in that case, the hint scheme is applied, which apply the L2 laws to close the intermediate responses of the teacher network and student network. So this hint scheme means we will apply the L2 laws in the middle layers of the teacher and student network as well. Okay, so but the thing is, the last layer of the network, this is teacher network, and this is the FinNet, which is denoting the student network. The last layer's dimension is always the number of classes. In classification, image classification networks, their last layer's dimension is always the number of classes. So if we apply the L2 laws to close this last layer, it is rather simple, okay, because their dimensions are already same as the number of classes. But the intermediate layers, if we want to close their response, then we have to fit their dimensions first. Okay, are you agree with this? So to relieve that things, let's say this is the teacher network's intermediate layer, and this is the student network's intermediate layer. Because their dimensions are not same, we have to apply another MLP layer, to make this, different dimensional vector into the same dimensional signal with the teacher model, and then apply the L2 loss like this. So actually, WR, this is denoting this MLP layer, and this is the intermediate layers of the student. So the dimension of this, and this is the teacher model's intermediate response. Their dimensions are different, so we apply one layer of MLP and then make it close. So this is the hint. And by applying this, when we train the student network by applying hint as well as the knowledge distillation, then and also we can apply that for the object detection pipeline as well. And also the knowledge distillation is taught from this kind of motivation. So the teacher is already pre-trained rich network, and student network, normally it is the faster architecture. Faster but comparable architecture we want to learn during the KD. But it can be also usable in this kind of scenario. So I told you, at the last part of previous lecture, I told you about this. So we want to achieve whole body pose prediction. So you are now maybe doing the assignment 2, and problem 3 is doing the hand pose estimation, right? So maybe you feel like that I'm assuming that you already seen the data. So to achieve the pose estimation, we have to label the skeletons by ourselves. Okay, so it takes time, and sometimes it is hard to obtain whole body annotation, because the image usually do not capture whole body, but instead capture only the hand or faces, or only the body without face or head. So normally the body dedicated model, or hand dedicated model, or face dedicated model, they can be trained easily, because the data sets are usually 2 for each domain. So we can train the body pose estimator using the body data, and hand pose estimator using the hand data, and face pose estimator using the hand face domain data. Anyways, this is the expert in each domain, and we somehow use this already pre-trained model as the teacher model, and by inputting some new training data to them and generate this kind of output, and we combine them to make this kind of whole body pseudo ground truth, and somehow train the new student network that can mimic this data. Okay, so this kind of thing also could be regarded as the knowledge distillation. So using this method, we can train the one single network that can do this kind of 3 tasks at the same time. Without data, we can achieve the whole body pose estimation. Okay, are you guys following this? So this is more result for that. And another thing is video pose is limited in the real world, okay? Because let's say you are given this kind of video, right? And let's assume that you are labeling this video for pose annotation. You can label most of the frames. Maybe if you have time, you can draw some point on each figure like this, and find their XY coordinate. Okay, if you have time, you can do that, right? For labeling the data, right? But for some of the frames, how to say, I don't know, but if there is too much pixels, which is not observed well, so how to say, let's say people are, how to say, let's say people are occluded, let's say some occluded by some object. Let's assume this kind of situation, right? People gradually, let's say in scene frame one, people are fully observable, but let's say he's walking in this direction, and after some frame, let's say he's uh, occluded by some maybe desk object, okay? Then he continually walk in this direction, and some other frame he again fully observable. Let's assume this kind of video is there. Then in this kind of frames, we cannot annotate, we cannot properly annotate the occluded body part, okay? So even though we want to spend time to label, I mean, this hidden annotate, hidden part, hidden body part, but we actually cannot know where is the exact their body part lies in, okay? Because of, I mean, the the objects that hide the body part, we cannot label properly for this frame, okay? So, I mean, this is some difficulty in labeling the pose annotations, especially for the video sequences, okay? We cannot guarantee all the body parts are visible in the video, okay? In all frames of the video. So we normally label the some of the frames in the video with where all the joints are visible, okay, to us, okay? And then we train the pose estimator and maybe apply those pose estimator to here, and maybe that pose estimator can somehow estimate some pose, I mean, which is hidden by the objects, and maybe we can later regard this as the pseudo ground truth, okay? But at the initial stage, we cannot actually label label these hidden body parts, okay? Are you agree with, understand this? Are you agree with this? Okay. Are you guys following this? So, I mean, that's, I'm explaining that it is hard to get the complete pose labels for the video, but for the frames, for the separate images, it is rather easy. Okay, we can just omit some of the frames which is hard to label. Okay. So in the community, there is less publicly available video pose data because of this challenge. Okay, so this paper, they want to train the video-based pose estimation pipeline, but they are saying that due to this kind of challenges, there's no complete video data for pose estimation. So they cannot simply train their video pose estimator using maybe the pairwise supervised, I mean the pairwise data set having both video and the frame-wise pose labels, because the data set itself is not complete yet. Okay. So instead, they apply some knowledge distillation-like way to extend the frame-by-frame pose estimation network towards the video pose estimator. So this is the teacher model. This is the pre-trained pose estimator. So what they do is, given one frame of the image, this pre-trained pose estimator, they estimate their corresponding pose. Okay. So I mean, like the problem 3 in assignment 2, you can train this kind of pose estimator for humans. Okay. So this is actually our pose, our teacher model, but our student network that have different input, actually having the extended input compared to the teacher model. So what we will input to student network will the current frames, current frames input, and also we will input the optical flow. Maybe some of you are not familiar with this optical flow, but optical flow that is encoding some flows of the pixels between two consecutive frames. So this optical flow is, this x of t is the current frame, and xt minus 1 is the previous frame. Okay. So by inputting these two images, you can get optical flow easily. So OpenCV, it already have the code, already have the function for calculating optical flow. So this calculates each pixel's flow. Okay. So somehow it encodes motion information for each pixel. Okay. So this is, I mean, previously it was very complex algorithm, and I mean, implementing this simple algorithm takes a lot of time, but now we can just call one function in OpenCV, and the algorithm is very reliable nowadays. So we can somehow encode the pixels flow across the frames. Okay. Anyways, this is encoding the motion. Optical flow is having the motion information, and x of t, that is our current frame's image. And our student network will input these two signals, okay? And then we'll estimate two things. No. Then it will estimate anyways two things, but following this decoder, actually the student network is composed of the feature extractor and then the decoder, and their output is having actually two vector. The first one is current frames pose, that is we will call P of T, that's the T frames pose. And also the second output would be delta P of T, which is PT minus 1. So the, I mean, maybe velocity, this might be velocity in physics. I mean, the difference between T's frames pose and T minus 1 frames pose, okay? So they will estimate both delta P of T and P of T, okay? So, yeah, but the ground truth for this delta P of T, that can be estimated from the teacher. So for the teacher, we will input xt minus 1 to get the pt minus 1. And if we input x of t, then we can get p of t, okay, current frames pose and previous frames pose. And then we find the differentiation of these two output, and that becomes the delta P of t. And this P of t corresponds to the one of the output from the teacher model. So anyways, we can secure these two from the teacher model. Okay, are you guys following this? So we directly apply the L2 laws to make the student network to mimic, to follow these two signals, okay? So now the teacher model and student model, they are having different input and output, right? Okay. So teacher model, it can only input one frame image and then estimate one frame's pose, okay? But using that information, we can apply two frames pose and we can apply two frames input separately, independently, and get two frames pose independently and get make the two kind of pseudo ground truths and use that to supervise the student model. Okay, are you guys following this? 이해되나요? 한 번만 더. 프리트레인드 이거는 이제 숙제 3번, 숙제 2번, 3번 문제랑 비슷하게 이 영상 하나에서 이제 포즈 하나 요 영상에 해당하는 포즈 추정하는 거 3번 문제잖아요. 이번에 그것처럼 얘를 프리트레인드 할 수 있고 근데 이제 얘에다가 인풋을 두 번 넣어보는 거죠. x 오브 t 현재 프레임도 넣고 xt-1도 한번 넣어보면 이전 프레임의 포즈도 나오고 현재 프레임의 포즈도 나올 거잖아요. 각각. 근데 요거 두 개 차이 구하면 그게 델타 p고 그 다음에 현재 프레임 그냥 쓰면 여기 p 오브 t 나오니까 요거 두 개를 어쨌든 티처를 두 번 어쨌든 어플라이해서 만들고 얘를 그냥 바로 추정하는 어떤 스튜던트 네트워크를 학습하고 싶은 거죠. 근데 인풋도 여기는 x 오브 t도 쓰고 옵티컬 플로우도 쓰고 그래서 스튜던트 네트워크는 티처 모델보다 더 확장된 모델이 될 거예요. So now the teacher model is kind of the extended model compared to the teacher model. The teacher model is frame by frame pose estimator, but the student model is the video pose estimator. Okay, considering two frames. Okay. 스튜던트가?
티처 뽑은 결과들이 되게 컨시스턴트하게 나오지 않을까?
뭐 그런 건 좀 있을 수 있겠죠. 네, 완벽하진 않겠죠. 네. 그렇지만 이제 어쨌든 뭐 한 프레임은 그래도 티처가 잘 한다고 어슈을 하는 거죠. 포지티브. Delta P. So somehow we are thinking that by estimating delta P, the model can understand more than one input cases. So their temporal smoothing. So yeah, we are enforcing such temporal consistency by using this additional output. So are you guys understanding this? Okay. So this is the P of t delta P I mentioned, and this is the feature extractor of the student model, that is F. Okay, and then apply this D, which is the decoder here, right? And this is the current frames input, and this is the optical flow that encode the pixels flows. So by inputting these two feature extractor first, and then input them to the decoder, this is actually saying the student network's output, and that should have these two vectors, which is the current frames pose and the difference to the difference between current and previous frames pose. Okay. So this is denoting the loss functions actually. So anyways, the lesson here is, using the distillation or pseudo labeling, you can even train a better network than the teacher model. Okay. And the other topic I want to share with you is the transfer learning. This is also very similar in the KD or pseudo labeling, but it is slightly different. Okay. It is similar to knowledge distillation in the sense that it is also using the pre-trained network. Okay, it is also using the pre-trained network, but it is not actually wanting to train additional student network, but it wants us to apply the already pre-trained network to a different but related problem. Okay, that's the transfer learning. So we already have some network which is pre-trained by some other data, but we want to apply this network, the same network, to different but related problem. That's the transfer learning. So somehow the transfer, keyword of the transfer is meaning that, okay? So yeah, the goal of the knowledge distillation, the KD, is provide the to additionally train the smaller model that serve actually the same task, okay, as the larger model. But transfer learning, it is applying the same network, the pre-trained teacher network, to some other domain. Okay, so they are similar but slightly different. So as I told you, the deep learning architecture, it is very deep and have many parameters. So to properly train it, we usually say million scale data, XY pairs are required. Okay, but sometimes it is very hard to secure this kind of million scale data set. Okay, because I mean, for maybe image classification task, it is rather easy because when getting the image classification label, it may take few seconds for humans, right? But for other more complex tasks, it may be hard, maybe take a lot of time, or even for occluded cases that I mentioned, it is even impossible to get the exact labels. Okay? So some domain, securing this million scale data is very hard. Okay, so with the aid of the transfer learning, we want to achieve relatively better accuracy on this kind of challenging domain whose data cannot be easily secured. That's the maybe objective of the transfer learning. So are you guys following this? The concept of this transfer learning is like this. So we first train the network. When we first train the network, it should be randomly initialized. And we somehow involve large-scale data, which is easier to secure. Okay. So for example, we learned about the ImageNet data. So in here, there are many images, and also there are 1,000 image classification labels. Okay. Not 1,000, I mean 1,000 dimensional the class labels. So there are 1,000 class. So each images are, I mean, one hot encoded with this 1,000 dimensional vector. Okay, so this is very large data. So we first can train this the network using this ImageNet data set, which is very large, and then we can apply the same network to other domains to fine-tune. By fine-tuning the model, we can by retaining the weight, most of the weight, we make another network. But maybe if that is the image classification task with the different number of classes, then we have to change it the last layer, okay, their dimensions, because it have to coincide to the number of class, right? So we normally retain all the weight pre-trained by the ImageNet dataset, but change the last layer to fit to the number of classes of the new task. Okay, and then for the tune, the overall network using new domains data, but this new domains data is their amount is limited, maybe. Okay, are you following this? And also, this is the example of implementing the transfer learning on maybe from the ImageNet data to the, the image classification using the small data. So, so you can see here, here is the AlexNet architecture we have already learned. Okay, so from the image, we apply several layers of the convolution and activation and pooling, and then we flatten the signal to the one-dimensional vector and apply a series of FC fully connected layers to map it to 1000 vector that indicate the probability for each semantic classes. So this is the AlexNet, and we first trained this architecture using the large scale ImageNet data. Okay, but let's assume that you want to do your own classification task by collecting your maybe your food. Maybe let's assume you are liking the taking pictures of the food, right? And then you collect maybe 100 images for your own food, so that you eat for last year, right? For example, then you now want to classify the food you will eat later based on the classes you already eat. Okay, let's assume this kind of scenario. So for that, you want to train the new deep learning network. But in that case, the deep learning network is very large, right? But so I cannot, especially cannot collect million scale data for the food classes that I ate. Okay, but in that case, the way you can achieve the image classification for the food you will eat might be pre-train your network, deep learning network, using the ImageNet data set first, and then replace the last layer to the C-dimensional vector. Okay, only replace the last layer to fit to your own application. Okay, let's assume there are 10 food classes you have in your data. Then the last layer have to have 10-dimensional vector. Okay, so by retaining all the weight from this pre-trained network, but replace only the last layer, and further train this network using your own small-scale data. Okay, then that will make this network to operate on your own data. Okay, are you guys understanding this? 아니죠. So C does not have to be some subset of the 1000 classes. That C can be any arbitrary number. Even it can be larger than 1000, but maybe the performance would be limited. But anyways, yeah. And also, we don't have to limit our new network to work for some subsets of the classes the ImageNet already have, maybe. Yeah, you don't, there's no limit. Yeah, but I mean, the performance could be better in the case. Yeah, if you constitute your small data set similar to the ImageNet, then the fine tuning may work better than not, the case which is not like that. But there's no actual limit for that. Are you guys understanding this? And if you go to this web page, then the PyTorch is already providing you the pre-trained network. Okay, so AlexNet, Vision&Learning, ResNet, and other architectures are already implemented, and also they are providing also the pre-trained weight trained by the ImageNet data. So you can freely use that by calling this one line of code. So the thing you can do is just call this package And then you can initialize your AlexNet by calling this one line of code. And if you indicate true for this flag, then pre-trained weight by the ImageNet data would be initialized. Or if you set flag as the false, then the random initialized weight will be used for the AlexNet architecture. So if you print your network initialized by this one line of code, then it can be visualized like this, right? But now if you want to do some transfer learning, so let's assume that your data is only having 10 classes, right? Then your last layer in previous ImageNet task was 1000 dimensional vector, but now you have to change it to 10. Okay. So this code is actually doing that. So you initialize the this is actually meaning the number of the index for each layer. So you can access classifier network, and there's 6th layer by doing this, and we define that for new MLP layer having 10-dimensional vector as output. Okay, you can implement the thing I mentioned here using this code, maybe. Okay, and also you can freeze. So actually, each layer have this requires on the background attribute. If you set this as false, those layers will not be for the trade. So that is actually meaning freezing the weight of each layers. Okay? You can use this, or if you think the earlier layers also have to be trained further, then you can also not apply this maybe. So, but normally, if your data is very small, retaining the earlier layers, which is rolling as the feature extractor, frozen, and only train the last part, last layer might be enough. But sometimes it is not enough, so you have to maybe also train the earlier layers by not applying this code. So actually, in problem 3 of assignment 2, you also have to do similar things, right? So we are requesting you to retrain, fine-tuning your network for the data set given, okay? So you may have to apply this kind of transfer learning techniques maybe, yeah. And the next thing is the pseudo labeling, okay? This is similar to KD, okay? So pseudo labeling, it means pseudo means to say the false, not false, is fake label. So it is, somehow not exactly labels, but you can regard it as the labels to train the networks. So in that sense, we are calling the labels as the pseudo label. Okay. Actually, we regard the output of some other networks output as the label. So in that case, we call that as the pseudo label. So, and we can use both the labels, original label, and also the label, the pseudo label. Pseudo label is some sense called as the unlabeled data because, in the data side, we are giving this labeled is having X, Y, the image X and their corresponding labels, right? But unlabeled data, it has only X, right? It has only the images, okay? But you will generate their corresponding label with the network already trained, okay? So by inputting this X, So this Y star might be given by applying X star to already pre-trained network F, right? So we can anyways, from the unlabeled image data, we can get their corresponding pseudo labels by applying them to the already pre-trained network. Okay. So as some of the students asked already, that pseudo label can be incorrect. Okay. But anyways, when training the deep networks, the amount of data that is more important. Okay. I mean, if the pseudo label is if their accuracy is above some threshold, if it is not totally incorrect, then getting more data might be helpful for training the network. I mean, yeah, compared to giving small scale data set. Okay, so people are doing this because of that. Okay. Okay, so pseudo labels are obtained from another network. So we will use the pre-trained teacher network, and for unlabeled image data, we will estimate their Y value, the labels, using this pre-trained teacher, and we will train the student network using both the label data and also the unlabeled data, but their ground truth is secured by the another network. Okay, that's the pseudo labeling. And actually, this pseudo labeling can be applied to self-training, and this paper is saying some very interesting phenomena. So what they do is they train first the teacher network with the supervised data where the XY are already given. Okay. And they are having also the unlabeled data only constituted with the images. And then you will infer their pseudo labels by using the teacher network already learned. Okay. And you will train the student model using both the unlabeled data, whose output is from the teacher model, and also using the labeled data as well. Okay, but this time you will inject some noises. Okay, so some noises in the image part. Okay, your image data will have, so this is also you have the supervised labeled data and also unsupervised data where its ground truth is coming from the teacher model. So this is your whole data to train the student model. But here you will apply some noise to this X during every gradient descent update. Okay, which means you will use this kind of data that the noise is applied. Okay, then in normal image classification training, if you apply some noises, then the network it means this kind of thing. For even noise images, your network is able to predict the correct label. Okay, in that sense, adding noise is giving some more challenging tasks to your network to learn. Okay, so in that sense, your network is becoming more robust in some sense, right? This is, sorry. So this is summarizing those things, the steps. So learn your teacher model and make the pseudo label for the unlabeled images and train the student network using both labeled and unlabeled data, but by adding some noise. then it means, so your original teacher models are their performance is this blue line, and this x-axis is denoting the number of parameters. So if you go this direction, it means faster and lightweight architecture, okay? And the y-axis is denoting the accuracy. So if you go to upper direction, that it means the network is getting better in accuracy, okay? Your teacher network is here, located here, but your student network using this scheme is like this. So it means your student network will be lightweight. At the same time, it would be more accurate than the teacher model. Okay. So actually, in the last step, what you will do is you will regard your student network as the new teacher and iterate this process. Okay. I mean, by iterating this process using regarding the new student model as the teacher model and label the unlabeled data and adding some noise and train a new student model using both unlabeled and supervised data. Your student network, by iteratively doing this, your student network is actually becoming better than your teacher model. Okay, are you guys understanding this? Okay. So this is actually very interesting result. Okay, given limited amount of labeled data, you can actually obtain better student model. That is faster and more accurate than the teacher model. Okay. So this is the example of giving the noise patterns. Okay. So this is the pseudo labeling, and one important maybe difference between pseudo labeling and the KD is closing the responses of the teacher model to the student model in the response level. Okay. But pseudo labeling, it makes actually the discrete label from the teacher model. Okay. In the sense that the output of the teacher models are used for training the model, they are having similarity, right? Pseudo labeling, they use the actual label information, but KD, that is closing the intermediate or the last layer's response to the student model. So we call that as the dark knowledge, right? Okay. So actually, this is very important. Will be in quiz 2. Okay. So are you guys understanding this? Okay. And actually, quiz 2, that will be in 11th of December. Okay. It is the last class before the final term exam. Okay. 12월 11일, December 11th. Okay. And the last topic is the self-supervised learning. In self-supervised learning, you don't even require any the label information. So we normally think we need both x and y value to apply it to the gradient descent algorithm. Okay, we learned like that already, but sometimes labeling takes a lot of time, and sometimes it is often impossible to get the correct labels. So to deal with such cases, the researchers are developing this kind of self-supervised learning techniques. Okay, so we can train the network without explicitly having this label Y, but we can use some indirect information to apply the gradient descent algorithm. So I will show you which kind of information we normally use. So, I mean, one important application of the self-supervised learning is you already know about the ChatGPT. Okay, so now the ChatGPT version is 4, and before ChatGPT, ChatGPT is application extension of GPT-4 to the chat application, but the core algorithm is actually GPT-4, and there was GPT-1 before, 1 to 3 actually before this GPT-4, and there was also the BIT algorithm, which is very similar to GPT in NLP domain. Okay, and as I told you, this T is meaning the transformer architecture. Okay, and actually they train this kind of these are called as language models. And what they do is they train these transformers to read a lot of language, the word data. Okay, and what they do is after training these language models with a lot of word data, they actually apply transfer learning that we just learned to the downstream tasks. So sometimes they can apply this language model to translation, or sometimes they apply to this to another NLP tasks and so on. Okay, so that's the concept of the language model. And how they train this large language model is using the self-supervised learning. Okay. And what kind of self-supervised signals they use is they actually apply 2 tasks for the using the word. The first is masked language model, and the next one is the next sentence prediction. So these 2 tasks is actually very simple. So the first one, masked language model, is meaning this is the sentence actually, right? They are using the 2 sentences always. The man went to, originally there was a word here, right? But they mask it, right? And went to, I don't know, store, but this is masked. And the next sentence is he bought a gallon something masked milk, right? So anyways, there was, originally there was 2 sentences without these masks, okay? But by applying these masks, somehow similar to context encoder in the assignment 2 of problem 2, from the original image, you can mask some of the patches, okay? And you can regard the masks as masked region as the ground truth, and the the image as the input to the network. So this is very similar to that. The original masked words can be regarded as the ground truth, okay? And this masked sentence become the input, okay? So from the raw data, you can by yourself generate the XY data. So, that's the first task. Your network have to infer the masked word from the unmasked word. Okay, that's the first task, right? So we don't have to generate any, we don't have to label, right, for this. Okay, we don't have to pay any manual effort to generate for making the labels. Okay, but it can be automatically generated. Okay. So that's the first task. And the next task is next sentence prediction. So it indicates if the 2 sentences are coming from the same, paragraph or not. So if the label is indicating that the two sentences are originally the consecutive sentences or not. If they are coming from the consecutive sentences, then this label is next. But if that is on purpose edited by us to attach it, okay, then it is we label it as not next. Okay, are you guys understanding this? Okay, if two sentences are originally, next sentence in the original data, raw data, then we call it as is text. But it is edited to be two sentences from some separated paragraph, then that we label it as not next. Okay, this is very simple things we can create. So using this tool, the BERT is trained. Okay, so the second task is just inputting these two sentences, and the transformer will infer whether two sentences are is next or not next. Okay, using these labels. Okay, and these labels, to create these labels, we don't have to pay any manual effort. Okay. So these types of supervision is called as the self-supervised signal. Okay. Actually, we are automatically create the XY data from the raw data. Okay. And language models are trained by this kind of two types of self-supervised tasks. And after doing this for many data, then language models are gradually become understand to the sentence, their structures, and also the meaning of the word. Okay, and then if we fine tune then language models to other downstream language tasks, then the researchers are observed that that works well. So that's the concept of the language models. Okay. So that is the self-supervised learning for the NLP domain, but in the image domain, because we are learning the computer vision now. Computer vision, there was also the self-supervised signals. Okay, and in this paper, researchers are proposing some self-supervision signals. So this is not actually the specific, these networks are not learned for some specific tasks, but the objective of the self-supervised learning is to supply many data, which can be easily generated from the raw data, and anyways train the feature extractor part of the network, and they later will apply some transfer learning, okay, to work for the specific tasks. Okay, that is actually the concept of the self-supervised learning. And their self-supervised task is, so let's say for this patch, let's say we are given from the images, we select this patch and we will input this patch to the, for example, the AlexNet architecture. And this part is shared. And if you also take another patch from this nearest neighbor location, neighbor locations. Anyways, if you select another patch and then apply the same feature extractor and then concatenate their responses, and in the last part, the thing you will estimate is this one of these 8 digit. Okay, so this is the classification task. You will estimate one of 8 locations, but this may, for example, is this second patch is located here, then you have to estimate 4, right? And if the second patch that is actually, if they are located here, then you have to estimate 5, okay? So by doing this, the network feature extractor that can be coming to understand their spatial relationship, okay? So, and for training this network, you don't have to pay any time for generating some labels, right? We can automatically make the data to train this kind of network from the raw data. Okay? So this is called as the self-supervised learning. Okay. And also there's another similar concept but slightly advanced that is publicized in the next year. Actually, they call it as the jigsaw puzzling. So they are similar, doing the similar things, but slightly in the complex way. So from the single image, I mean, this is the original index, but how to say, okay. So you can input, I mean, so I mean, here, as far as I understand, there have to be 9 architectures applied in this jigsaw puzzling, but there's no, I mean, the, yeah, here there's some figure for that. So these architectures are actually shared. This is the feature extractor part, okay? And you apply this feature extractor for nine times, okay? Okay, here. And then you concatenate their response and map it to some classes, right? But what they actually estimate at the end is their permutations. Okay, so I mean, their orders could be in the, I mean, in random, could be in the random. So in the last part, it had to estimate their orders. So let's say this patch is 9s, and this patch is 4s, this patch is 6s, and so on. So this kind of permutation, you have to estimate in the end. Okay, are you guys understanding this? Okay. And this permutation that can be also automatically generated from the raw image data. Okay, in that sense, it is called as self-supervised learning. And by solving this jigsaw puzzling, the network, the feature extractor becoming to understand spatial information. Okay, but actually they do not. Actually, if there are 9 patches around this one center patch, there are 9 factorial possibility of this permutation, okay? But they only use the 64 cases because this, by constituting the last layer into 9 factorial dimension, that's too big, okay? So they actually select only 64, how to say, I don't know how to, but they select the 64 permutation cases and only constitute the last layer with the 64 dimensional vector. And they, anyways, found that that could be a robust self-supervised signal to train the network. And another self-supervised learning technique is predicting the rotations. So this is similar to data augmentation. So given this original image, you can rotate those images, and then you can train the network, their feature extractor, to estimate how much they are rotated. Okay, that could be also easily generated from the raw images. And So in that sense, it is called as the self-supervised learning. So here, jigsaw puzzling and context encoder, maybe, context prediction. We learned context prediction, maybe not in here. Jigsaw puzzle, and anyways, this network is called as LootNet and jigsaw puzzling. But this simple scheme is actually better than the jigsaw puzzling. So it at 2018 rotation network, that is the somehow state-of-the-art self-supervised learning techniques. Okay. And for videos, there are another self-supervision learning techniques. And nowadays, this contrastive learning is very popular as the self-supervised learning techniques. But maybe we can continue this next Monday. Okay. And also next Monday, we will start learning about the efficient object detection pipeline. And actually, that would be the last topic. Okay. And then the next Wednesday, we will have the quiz 2, and that will be the final of this class. Okay. Anyways, thank you, and see you next Monday.